Hello, everyone. Welcome to the workshop today. This is a workshop on LCO and photometry. There's light coming behind you. Yeah, so I'm Priya Hasan, and I have Najam Hasan over here, who's helping me close the window. And welcome. Today, what we're going to have is these are two short sessions, 2-hour sessions today and tomorrow, on which we talk to you about photometry as well as I'll mute everyone. I'm sorry. If you would like to say something, 1 second, I'll just mute everyone. But you are most welcome to give your comments or say something. Muting is, we still encourage you all to talk to us, but this is just for convenience. Please write something on the chat if you want to speak. Yeah, now you can do.
Yes, so hello, I am Hasan, Najm Hasan, and I hope you benefit from this today interaction with you. And we hope that this will continue like we have done it in our previous workshops. This is where we introduce you to the basic concepts, ideas, and then you start working on it. And as you require help or assistance, we'll train you through other aspects of working with the LCO data. So thank you. Over to Priya.
Yeah. So we'll start off with the very basics, which we are going to talk about today. And that is essentially on photometry. And I hope it's not repetitive for the others, but I'm forced to do that. Okay. So like I mentioned earlier, our workshop today is on LCO and photometry. And LCO is basically the Lascaux Rays Observatory, which you can see over here. It's basically a set of 25 telescopes which are located at 7 different sites across the world, which you can see over here, and they work together as one instrument. And the idea of it being that you are giving, these are small telescopes, they're only 40 centimeters, but the idea is you have access to all these telescopes at different locations all over the world. So if there's something you want to track or something you want to observe urgently from any part of the world, you can do it from these sources. And we can actually help you to access the data, access the telescopes, so that you can use it for your purpose too, right? So I'll start off with, yeah. So like I told you, the plan of the workshop is today we talk a bit about photometry, what is standardizing photometry, what are CCDs, what is the LCO, what is the Banzai pipeline, that is the Banzai pipeline which we have for LCO data. And then if time permits, we'll do a hands-on demo session with the Banzai output. If it doesn't permit today, we'll be doing that tomorrow. And we'll be showing you on how could you handle the Banzai data, number one, through something called TopCat, which is a virtual observatory tool. And secondly, show you how to use that using a Jupyter notebook. And if you're doing it through a Jupyter notebook, you'll have much more freedom. You'll be able to plot things. You'll be able to, visualize, analyze your data with much more efficiency. Right. So pardon me for something. These are basic things which some of you all may already be aware of, but I need to do that just for completeness, because some of the people participating in this workshop are also amateurs who want to use robotic telescopes, and therefore I'm repeating this thing. So first of all, let's start off with what is photometry. So photometry, Greek photo means light and metry is to measure. So essentially it's nothing but just measuring the light of astronomical objects. Now there are other things one can do with astronomy observations. It's just not photometry. The more powerful method is spectroscopy, where you actually analyze the light with respect to the different wavelengths you're getting it. You could also be doing polarimetry. That means you're measuring the polarization which you get from objects. But in today's workshop, we are basically going to focus on photometry. Okay, I promise you we'll have another one on spectroscopy, but this one is on photometry. Fine. So the simplest thing is that light, when it passes through a telescope using a photometer, we use various electronic devices. The earlier people, what they used was photometers, and now what people use is CCDs. And this basically gives you a measurement of that light. So a photometer basically works on the principle of photoelectric effect. So what happens is as light falls onto the photometer, it basically generates an electric current. And then what we do is we calibrate this current, okay, with respect to standard stars. So there are standard stars which are observed, and you measure, what is the brightness of those objects, and you use that to scale the brightness of the object you are actually looking at, so that it gets scaled. And in that way, we can actually move on to First of all, what we call apparent magnitude, and then even absolute magnitude of celestial objects. So a photometer, you can actually put it onto your eyepiece. If this is a telescope, you will add on your photometer here at the eyepiece point. And essentially what you have is, it's a very simple mechanism. You have the light coming onto this. If you want, you pass it through a filter. If you want to measure the bright coming from a certain, in a certain wavelength range. And that light that falls onto a photocell, from which you get the reading on a galvanometer, right? And in that way, you can actually see what's happening, and you will be able to, measure the light which is falling on it, right? I hope nobody has any problems in this thing. Okay, yeah. So, before this, there's another slide. Yeah. So here, yeah. So first of all, what is the brightness of a star? So if you have a star, what is the brightness below? Where does the brightness come from? So essentially, you have two factors. One is the radius of the object, which defines the surface area, and the other thing is the temperature to the power of 4. So we have this from Stephen Boltzmann's law, that you have 4 pi r squared, assuming them to be a sphere. That is your surface area, and then you multiply it by sigma, which is Stephen Boltzmann's constant, which is given over here. 5.67 10 power minus 8 watts per meter squared per Kelvin power minus 4 multiplied by T power 4. So what you can see is that these are the two important factors, the radius of the star as well as the temperature of the star. And then the next important factor to the brightness, which comes to us when we actually observe this, is when we actually observe it, what we actually see is the distance factor. So all these objects actually follow what is called the distance square law or the inverse square law. And basically what that means is that if you have a star and you draw circles, concentric spheres around it at different distances, there is a decrease in the luminosity as a square of the distance, right? So you'll have a 1 by d squared factor, which comes in because of the distance to the star. Okay. Now, to measure this brightness, there was a scale which was given a long time back, and basically that's the magnitude scale, which actually was used to define the brightness of stars. So way back into BC, Hipparchus actually classified stars on the basis of their brightness. Okay, so in this case, he actually called stars magnitude 1, 2, 3, 4, 5, 6, where 6 magnitude stars are the faintest. So you start off with first magnitude star, which are the brightest. So these are kind of like importance, right? So the first important star is the star which has the magnitude 1, and then you move towards magnitude 2, 3, 4, 5, 6. And typically 6 magnitude stars are the stars which we can see with our naked eyes. That's the best we can get, right? But generally, most of us who are bound to cities and to much more, a lot more light pollution, etc., you obviously do not go to 6 magnitude, you go much lesser. Right. So like I mentioned, the other important thing is that the response of our eyes actually follows a logarithmic scale and not a linear scale. So for example, if I were to multiply the brightness of stars, say there's a magnitude difference of 5 between 1 and 6, right? I repeat it, you'll actually see that this goes as a factor of 100 times brighter. So actually, if you were to look at two successive classes which would differ in terms of apparent magnitudes, you'll get 100 to the power of 1 by 5, which is 2.512, which is the factor of brightness between the brightness of magnitude 1 and magnitude 2 stars, right? And yeah, so some people have asked for copies of the slides, etc. Yes, I will put it up on that website, and you're most welcome to use the slides, right? So I'll be sharing it, right? So what happens is, this is something which we need to remember very well. Like I said, that 5 magnitudes corresponds to a difference of about a factor of 100 in brightness. And we need to remember that this is essentially a logarithmic scale, which we have for brightness. So each magnitude corresponds to this factor in difference in brightness, right? The other important thing, like I told you, was the brightness factor. Like I said, there was sigma 4 pi r squared t power 4. The other important factor is the factor of parallax, right? So parallax is basically is the distance, right? I told you that the brightness of the star will fall as 1 by d squared. And therefore, it becomes very important for us to, if we want to know the intrinsic brightness of a star, it is very important for us to know the distance to the star. Now, the simplest method to find out distance, and that's exactly the method which our eyes itself use, our bifocal vision, right? What do we do with our bifocal vision? We basically have a baseline, which is the distance between both our eyes. And when we look at an object, we are essentially seeing the angle subtended by both the eyes. And that is what we call the parallax angle. And the parallax angle, in principle, if I define it, that can actually give me my distance. So the simplest method we can do is, for example, while the Earth is going around the sun, you look at the position of a star today, say in January, and then after 6 months, while this is one astronomical unit, which is the distance of the Earth to the sun, 150 million kilometers. After 6 months, when the Earth comes on to this point, you look at the position of the star, and half the angle is the parallax angle. And it's very simple to see that if you do it in astronomical units, you can actually see that you will get the distance is 1 by p, right? So in that way, you can find out the distances to stars. So in that way, let us assume that we know the distance to our object, right? Like I mentioned, parallax is nothing but 1 upon d. And in this case, when we actually do our angles in terms of an arc second, right, then your distance you're going to get in the form of a parsec. So that is the unit of a parsec. So a parsec is the distance of a star at which it's going to subtend a parallactic angle of 1 arc second, right? Now what happens is, let us go ahead. And the other thing which we need to remember is, in the magnitude scale, there is what is called apparent magnitude, right? Is apparent magnitude. And apparent magnitude is obviously the apparent magnitude, the brightness that it shows to us. And the important factor in apparent magnitude is the distance factor, right? So let us assume that we look at an object, we do not know the distance to that object, right? So we see a certain brightness, which is what is apparent to us. But obviously the intrinsic brightness of that object may be very, very different, right? If the object is very close to us, it may appear more brighter than what it actually is. And if it is further away, it may look, it could look fainter, but it could be actually a very bright object. And therefore, here on the scale, you can see I have marked the apparent magnitude of various objects. So since the sun is so bright, right, you see the apparent magnitude of the sun is minus 26 in the magnitude scale, which I had shown you. Remember, the magnitude scale which I showed you has a reverse, this thing. So minus 26 object of magnitude minus 26 is much more brighter than, for example, an object of minus 4, right, or 2 or 6. So the sun has a magnitude of about minus 26. The full moon is minus 13. Venus is minus 4. Polaris is 2. Naked eye limit is 6. And there you can go ahead with that. So we need to remember that what we are actually looking at is apparent magnitude. And if we want to change apparent magnitude to absolute magnitude, the important factor we need to do is distance, right? So if we write this simple equation that this is in terms of any two stars with apparent magnitudes B and A, if we replace it by what we call the absolute magnitude, right, then the absolute magnitude is the magnitude of a star at a distance of 10 parsecs. Okay, so therefore what we do is we shift it to 10 parsecs at a distance of 10 parsecs. And in this very formula which I showed you previously, instead of this, I put my distance at 10 parsecs and I put this as my absolute magnitude. And therefore I can get m minus m. You can see the formula over here. Okay, it will come in the next slide, where you'll actually see the absolute magnitude, where m minus m is minus 5 times 5 log d. And here, for example, if I were to place 10 parsecs, then you'll get minus 5 plus 5, which is equal to 0. So m is equal to m, and that is nothing but the absolute magnitude, right? So in that way, you can find out the absolute magnitude of two objects in this way, right? Okay. Fine. Now, so we can go on to absolute magnitudes. The other important thing is, how do we measure this brightness? So we measure this brightness, if you're looking at a star, using what is called aperture photometry. So let's say we have an object over here, right? Which is the object we are looking at, say the star. Now what happens is we yeah. So what happens is if I actually around the object which I'm observing, I actually draw two annuli. Okay, one is what I can call the inner sky, the outer sky. So then this annular region, you see, this is what I do to sample the sky. Right? It's very, very important for me to have the brightness of the sky, because when I'm measuring the brightness of the star, I have to subtract the brightness of the sky, because otherwise I am going to wrongly estimate the brightness of the object. So for my object, I find a region around it, which is an annulus, which is the sky, and I subtract that brightness from the brightness of the object. And this is what I called aperture photometry. So I draw an aperture in which I assume that all the light from the star is filled, like this white ball over here. And then I take a region around this, right, which I call my sky. Okay. And therefore, I need to sample the sky. This is the background annulus. This is the photometry aperture. So I first measure the flux within this white circle, which is the flux from my source. And then I take it within the red annuli, which will give me the background. Now, what I'm going to do is from the source, I'm going to subtract the background. And with that, I will get this amount of brightness which I have of this source. We need to remember this, because this is how we measure the brightness of any star. And typically, that's what LCO also does. They get muted. Yeah. The other more correct way of measuring the brightness to stars is by what we call profile photometry. Now we know that every star, in principle, it spreads its light. Okay. So this is the profile of a star. If you have a star, which is a circular star, in principle, it gives you a profile like this. So when you're taking aperture photometry, you're slicing. Okay. And depending on the size of the slice, you are slicing it. Supposing I take a very small aperture, that means I slice it over here, right? And if I sliced it over here, that means I've lost all these photons which are sitting over here in the outer region. So if I take a very, very small aperture, the slice is underestimating the brightness of the star. If I come down, I will take this, and depending on how much do I get all the flux. So ideally, the deal is how well do you draw your aperture so that you get all the flux of the object you want, right? And therefore, we have to put this flux differently, right? But the problem is that you can look at these stars over here, all of them have different brightnesses, right? And therefore different kinds of profiles. You see this kind of star may have a very broad profile, while you could have a fainter star which has a very narrow profile. And therefore what is done is, if we did aperture photometry with this, you will do it with some average values. I'll just take my questions once I finish this little part, okay? Arjun, just 2 minutes. So therefore, what happens is, depending on where I cut this, there's going to be a problem with my aperture photometry. And therefore, what is done in profile fitting is that we take some good stars which have a good profile, which we essentially call the point spread function, okay? So we take good stars which have a good point spread function, and we scale every star to that point spread function, so that we can, if we do that, we can effectively get all the brightness of any star, right? Which is, for example, any of these stars. And therefore, profile fitting is a more correct way of doing it, but it obviously is a little bit more computationally expensive. And therefore, typically for LCO data, which we are going to talk about today, robotic telescope data, in this case, what happens is all the observations are automated, as well as the data pipeline is also all automated. And therefore, the profile of stars can vary every night, every day, depending upon the seeing conditions. And therefore, it's difficult for us to actually characterize the profiles. And therefore, what is done with LCO data is aperture photometry, not profile fitting, though that is the more smarter way of doing it. The other important thing we need to know about photometry is that in astronomy, we also add filters, okay? That means we measure the photons which are coming in particular wavelength ranges. So you will see when we are applying today, you will see we'll apply different kind of filters when we actually want to observe, right? So the most standard filters which are used are the Johnson-Bessel UPV-RI filters. So essentially, U basically stands for ultraviolet. This is for blue. This is for visual, for red, etc. And you can see that these are filters which are, like for example, this one is quite narrow. You can see it has a width of less than 100. This would be in nanometers. Okay, this is in nanometers, so it's about 100 nanometers. You can see blue is a much more wider filter, where I have something more like this. B is like this, I is a much more broader filter. So all these filters have different characteristics, and they're specially designed to be around certain spectral features or certain phenomena, and accordingly people choose their filters, right? So either you can have a broad filter, or you could have a narrow filter. For example, people have filters around the H alpha line. So the H alpha line is a typical signature of young stars. So if a star emits in H alpha, it's a young star, and therefore filters can be designed for certain characteristics, or they could just be broad filters which can give you the presence of stars, right? So it depends on that. So we are also going to be dealing with filters today, which you'll see with the data. And so that's it. I'm going to take my questions first before we go on to the next topic, right? So I'll just look at the questions. Sarah is asking me about a copy of the slides. Okay, I'll upload the copy of the slides on our website, which I'll send you mail and link about, so you'll be able to get this thing. So you all will get the slides, not a problem. And I have a question from Arjun. What physical quantities in this axis, in this 3D plot? Arjun, could you just mention which 3D plot are you talking about? I am going to give you permission to unmute yourself, so you can unmute yourself. And I didn't understand.
Hello,
Yeah.
ma'am, you were talking about the profile photometry, I think, and there is a 3D plot of the profile of the star, and I'm asking about this plot, I think. So what are these?
Yeah, so this is actually just a 2D field. This is a field from the sky. Sorry, it's in bad resolution. I should have got it with better resolution. This is just a set of stars. This is a cluster, I guess, which has a set of stars. So this is a 2D picture. This is not a 3D. This is a 2D picture of a cluster of stars. What you're seeing on the left, this is 3D. This is an image of the profile of a star. So what happens is, what you're seeing in 2D as a star, right? In reality, it is basically a spread out image of the star. So a star, what happens is, it does not occupy a dot, right? We know that the star is not resolved. So in principle, a star is, a spread out thing. And in astronomy, we call that spread out thing, we call it a point spread function, right? And this, what you're seeing on the left, is the point spread function of a particular star. So a particular star is actually spreading its light over this whole region in reality, right? So it's basically an effect of diffraction of light because of that, as well as in this case, what happens is, the point spread function is not just diffraction, but it's a whole response of the telescope, the filters, the whole optical setup, whatever optical setup you have, this causes this to spread out. So we call this a profile of the star. And that's why I told you that then when we are selecting the aperture, right, we need to see what part of the profile you are seeing. So if I were to take a small aperture, I will not get all this light. So I need to correctly choose my aperture so that I get all the light. So I hope that answers your question, right? This is the
Yes,
profile of
ma'am.
the star.
Yes, ma'am. Just I want to mention that, is it something like the Aries-Dix function that we get from the far field diffraction?
Kind of. But in this one, there is also a result because of the optics. It's in Aries disk, it is pure diffraction, right? 1.22 lambda by 2.
Yes.
That is what you're getting in Aries disk. In this case, what happens is that coupled with that, you have an whole optical system, which is the telescope and the filters and the response and all those things. So in the point spread function, the effect comes because of all these effects, right? Not
Okay,
just
thank you.
that, it's all that, right? So it's all put together. Yash is asking me about this, and I'll explain this to him about JHK filters. So what happens is, traditionally we had the UBVRI filters, which so I'm muting all. So If you want to speak, please let me know. I've muted all just for this thing because we have about 100 participants and I need to do this, right? So what happens is, earlier when the filters were designed, they were U for ultraviolet, B for blue, V for visual, R for red. And then what happened is, as we went to longer wavelengths, people added on more these things. So then what happened is, after I, people then went in alphabetical order. So then you had the JHK filters, which you're asking about, which continue from this. So actually, J filter is 1.2 microns. That's J filter. H filter is 1.65, and K filter is 2.2 microns. So what happened is, after I, people then added the usual alphabetical order. So it becomes I, J, H, K, L, M, N, O, P. It goes in the normal alphabetical order. Though the beginning ones, U, B, V, R, they are not in alphabetical order. But after you go to I, then J, H, K, all of them go in alphabetical order towards increasing wavelengths. So JHK are near infrared filters, which we can do with ground-based telescopes. But then when you go to LMNO, L can be done in very special sites, but longer wavelengths, you cannot do it on ground-based. Essentially because the atmosphere covers it all up and we do not get, they don't pass through our system. So we do not. No, these are longer wavelengths. So like I said, J is 1.2, H is 1.65, K is 2.2, and L, M, and on go to mid-infrared, far infrared, etc. So it's all longer wavelengths. Madhu, yes, the meeting is being recorded. It's on our YouTube site. So it's already in live streaming, because the problem is we had more than 500 registrations. So the Zoom we have will only accommodate 100 people. So the remaining people have to see it on YouTube. So we are then, people will see it on YouTube where there's no restriction on the numbers. So I'll just finally, you all are most welcome to put your questions on YouTube also. So I'll just have a look and just see. I think all the questions are answered on Zoom. I'll just see if there are any questions on YouTube which need to be answered. I don't see anything just now, but there are people watching it. So please, people who are watching on YouTube, you're most welcome to add your questions on the YouTube also, because our Zoom is only letting in 100 and we already 99 on Zoom. So more cannot fit. Remaining are on YouTube. So thank you very much. I think I told you about the basics of photometry. And now we are going to Najam, and Najam is going to continue. He's going to talk to you about CCDs. These are charge coupled devices, and these are basically the devices with which we are measuring or getting our data on these telescopes. So over to Najam, he'll talk about CCDs. You are. Okay, just 1 minute. Yeah. So, and where are you? Okay. Okay.
Hello. Yeah. Hello. Yeah, this is Najam, and I'll be talking about CCDs. Yes. Here's the presentation. So CCDs, as we know, it stands for charge coupled devices. I think there's a big mess up, No. Yeah. See that? I don't know somewhere. Hello. It's behaving strangely.
Yeah, can you send me the presentation? Your presentation is on.
Yeah, but I see my screen is totally messed up.
Just share.
Can you see it?
No, not yet. Are you sure? Yeah, just hold on with some technical problem with this thing. We'll just.
What's happening?
Are you sharing your screen on?
Just see now. I think this is better now.
Yeah, now it's fine. Go on. Start. It's fine.
Yeah, so charge couple devices. There's some problem.
Start talking.
Wait.
Huh?
I'll have to go out. You just talk to them and re-log in.
Yeah. Yeah. I'm sorry, there seems to be some little technical problem. We are addressing that at present. So, yeah, I'll just. Meanwhile, I'll start talking to you all about LCO. Okay, let's talk about LCO and then we'll get back to this, right? So,
Hey, Priya, wait. Now I can't see that.
So let us talk about LCO, which is what we are going to talk about. And this is essentially the last Kumbh's observatory, right? Which we, like I told you, it's a series of 25 telescopes at 7 different locations. Much of you, I'm sharing my, are you sharing?
I'm sharing now.
But I was sharing, okay. I'm sorry, just a minute, please. I'll do the LCO thing and then you do CCDs. Email me the thing.
Absolutely. Yeah. Yeah, okay. So we'll be looking at the charge couple devices. The optical sensors used in astronomy are various, but I'll be talking to you about the 3 basic ones. The human eye. We'll be focusing more on the third one, right? The first one is the human eye. Human eye has played a very big role in observational astronomy for most parts of the observational astronomy, but it limits sensitivity. There's a limit to how faint we can see, and then the other issue is the subjectivity. What one person sees as a bright object, the other may see it as faint, and there is a lot of subjectivity involved in it, and it has serious limits on what could be discovered and so on. A great step in astronomy was the advent of photography, and photography led to observing unobserved things which could not be seen with the naked eye. If you could take long exposures with with a camera attached to a photographic plate attached to a telescope, we could image objects which could not be seen by normal eyes, naked eyes. Second thing what photography added is objectivity. You could record this and there was no subjective element of the observer, but what got recorded was what we saw. And but there were issues with photography too. The efficiency, even though it was more efficient than the light, than our eye, the efficiency remained pretty low. For example, for every 100 photons that strike a film, at best only 3 or 4 react with the photographic emulsions and so on. And secondly, photographic plates are sensitive to certain lights and not to the others. So for certain wavelengths like the blue, photographic plates were more sensitive, so they would record blue light better than red or so on. Then comes this charged coupled devices, CCDs, which we shall be talking about. So what are CCDs? These are these digital cameras which we use. We have CCDs in our mobile phones, we have it in our digital cameras, but the CCDs which astronomers use are more sensitive to light and they are more sophisticated. So CCD image essentially is a two-dimensional array. And like you see in this pattern, you have pixels. Each block is a pixel, a picture element, which records light which falls on that. And it's a two-dimensional array. And depending on the kind of CCD you may have 1K by 1K CCD, number of rows and columns are 1024 by 1024 or 2K and so on. And we use the various filters which we shall see further to construct colored images from CCDs. Otherwise, CCDs give you only black and white images. And by using artificial colors, we could construct colored images. So the advantages of CCDs are these, that they are very sensitive. The quantum efficiency is very high. It can record very faint light as well as it can record very bright light. Right? So sensitivity is large, while photographic plates did not have this kind of a sensitivity. If the light was too faint, it would not get recorded on a photographic plate. And if it's too bright, then it saturates the film and the whole thing gets saturated and blooms. So CCD has that advantage. So it's very sensitive. Short exposures get recorded, long exposures. Secondly, the dynamic range. What I mentioned is the dynamic range, recording very faint light as well as very strong light. And the most important thing is CCDs have a linear response. Like Priya mentioned, the response of eye is not linear, it is an exponential response. But in CCD, you have a linear response. So this comes to our advantage in the sense that if, suppose you are taking an image of an object which is reasonably bright, and we are giving, say, a 30-minute exposure, and if it's saturating, it's the amount of light collected is a lot and the whole thing is saturating the CCD, then you can take 3 10-minute exposures and add them up, right? And this addition, subtraction of images becomes very much simple because, as we have seen, a CCD is nothing but a matrix. Exactly like you have a matrix where you have a two-dimensional array. Each pixel records a number of photons, and that count gives you how much of light which has fallen. So if you have two matrices, you can add them up, and the matrix addition is our usual one, where you have A11, the first element adds up with B11, the first element of the second matrix, and A12, the second element, first row, second column adds to the first row, second column one, right? And similarly, you can subtract one. So same way you can do flat fielding and division. So we'll come to this. And CCD's quantum efficiency is almost about 80% to that of the photographic plates. And this graph shows how the different, what is the eye limit, which is shown in the lower curve, how the photographs are sensitive. So if you can see in this wavelength radiation graph, you can see that I can record light from, say, somewhere at 4.8 to 6.3 or so. But yeah, the wavelength in while you have photographs which go from 0.3 to 0.7, and photometer tubes, they have a larger one. And we see that this thin CCDs go from all the way from 0.3 to 1 point, it extends further up to almost 3 and so on. So its quantum efficiency is very large, dynamic range is very high. And you see the quantum efficiency of an eye, it is less than 1. Photographic plates are slightly more quantum efficient, while the CCDs are much more, almost 80% more than that of the eye. So astronomical images are essentially two-dimensional arrays of values. Ideally, the value of each pixel is directly proportional to the amount of light that falls on that pixel during the exposure time. But practically, that's not correct, because we will see that when you are recording light on a certain pixel or on a picture element, we'll see that the sensitivity of each pixel will be different. There may be thermal background which gets recorded. So it's not just the light which is coming from your object, but there are other light and other currents which get recorded. So though practically we say each pixel records light falling on the pixel during the exposure time, but it is not quite correct, right? And we'll understand as we go further ahead. And we'll come to this again later. CCDs just record numbers. And when you construct image from that, you get essentially black and white ones. But if you take images in more than one filter, then you can have this RGB combined and construct colored images out of which one. So you are taking an image of an object through, say, a red filter. It lets in only the wavelength, red wavelength come through. And when you remove the red and put the blue filter, it will let the blue one come in. So depending on the amount, if the object itself is blue, then the blue filter would give a higher reading. So the counts which you get from the blue filter is higher than that in the red. And that way you can construct these images. So you require preferably from 3 different filters, and you can construct these images. So what do we record on CCDs? We have to differentiate between these counts, photons and electrons. So the number which is stored in a raw astronomical image, right, straight from the telescope, is called the ADU, the analog digital unit, or that's called the count. Internally, the camera converts the analog voltage in each pixel to a numerical value, right, which is the count which we have. The counts of interest to astronomers are the ones generated by the photoelectric effect when a photon hits the detector. And the number of photons or equivalently electrons that reach the pixel is related to the counts in the pixel by the gain, right? And the gain is typically provided by the manufacturer of the camera and can be measured from a combination of bias and flat images. So we'll come to see what bias is and this. So we have to note that not all the counts which get recorded in a raw image are important light, right? So bias is an offset voltage which is applied to the CCD chip to ensure that there's no negative counts during the readout time. And there's small variation in the value of the bias across the chip, and they may vary over time also. The bias over the same chip over time could vary, and it is essential to make record of this bias. Then we have something called the dark current. So counts can be generated into a pixel due to thermal motion of electronics in the CCD. So even if you have your telescope covered, your camera covered, you're not exposing to any light, but if you take an exposure of, say, if you're going to image that object for 30 seconds, then you take a dark frame, keeping your shutters closed, and you record, you get some kind of a thermal image which comes on your screen, in spite of no light falling on that. So this is called the dark current. And then there is this intrinsic noise due to the electronics of CCD, which is called the read noise. And if you are imaging, say, a star cluster, you may also record, you in fact record even the light from the surrounding region or the scattered light. The sky itself has a certain brightness, and even that gets recorded in the frame. So you have to subtract this sky background as well. And then you have these cosmic rays which hit this, though the chips are extremely small, but these cosmic rays come and hit it, releasing charge, and that gets converted to counts, and you get an image which gets recorded. And one needs to realize that CCDs are also not perfect. They are tried to make it as perfectly as possible. Each pixel may have a different response. The
Sorry,
same
sir,
light
someone
falling on
is
different
unmuted,
pixels may
please. It
have
is
different
causing a lot
counts
of
that get
disturbance.
registered. Right, so there are various issues which come in with the intrinsic construct of the CCD. And there are a number of issues that some of which can be corrected, right, while one of these is the vignetting, which is the darkening of the image in the corners, which is a common thing, which you see it in this image. The edges are vignetting, which is a common thing and which can be corrected. Then, if there is dust in the optical path, right, or in the lens or on the mirrors, then it can create these donut and worm type of blobs. For example, you see it in this frame. Yeah, the dust. Then, like I mentioned, the variation in the sensitivity of the individual pixels can also create a problem, and this can also be corrected. Right? You can have various different images, and a sensitive pixel can.
One second, okay,
I'm not.
She said she can't hear. Just can't hear. Anyway, talk.
And then there are these dead pixels, which are pixels that don't respond to light at all. And you cannot do anything regarding that. Only that you can take images, the third images, so that if you have lost a certain part of an object in a certain image, most of these errors can be corrected by which are called the I hope you could hear me all this while. Yeah, so most of these issues which come up with the CCD, they can be corrected by flat fading. Yeah, these are called the flat corrections. And many of these effects, errors can be removed. So here's an image which shows all the errors which should come through. And we can make corrections. Yeah. So here, look at the image. We have two images. One is the image where you have the vignetting effect as well as the sky brightness, and you have the objects with the stars which we have imaged. And on the left-hand side, after having removed uh, these effects, I can create an image which is much more sharper and much more better. Okay. So image processing is an art by itself, and we can see how these raw images are constructed. Basically, the bias, noise, dark currents, all these add together when you are taking an image. So, and making a good image out of the one which we have acquired is done in the following way, right? So, raw image is essentially the sky and the star which we have here. So we have the stars, and when you image, you also image the sky background, and then you have the dark currents. That is the current which gets recorded on your CCD, even when you don't expose it to any kind of light. Then there is this noise which is inherently there because of the electronics of the system and various things. And then we have the bias which we have spoken about. So this is the acquired image, the raw image which we have. And what we are interested in are essentially the stars. Yeah, so at the moment I'm keeping the star and the noise together. And here you see you have the raw image and you subtract the bias from it and you remove the dark current from it, right? So this will give you, see, the image which you have taken, and you remove that aspect which is getting recorded on your CCD, even when there is no light exposed to it. That is the dark current. And then you remove the bias which is given. If there are negative currents on the CCD, there's a voltage which I had mentioned when I explained what bias is. So that has to be removed. And then you divide it by the flat. And the flat is you take many images of evenly lit screen. So flats are made up either by at the time of twilight, just before after the sun sets and before the first stars appear, many images of this sky, which is a very homogeneous sky, many are taken and the flat is created. So flat can be created by taking the mean of these multiple exposures or by taking the median of it, right? So it is, or there are certain evenly lit screens in your telescopic dome, and you take images, and then you see that though the screen, the object which you are imaging is a homogeneous spread of light, but when you are imaging, your CCD is recording some features on it. So with many of these, you make the flats, and when you divide from the flat, you get rid of this image from your, yeah, and then you subtract the sky from it. So that gives you the stars and the noise. And it's very often it's difficult to remove the noise. So if you take multiple exposures, then the noise, because it's random, you can stack them up and then you can minimize the noise in it. So dark currents are calculated from dark frames in the following way. So I'm putting noise all through. So you have dark frames minus the bias, and then you divide it by the dark exposure time. Okay. What we see here are a host of different filters. Priya spoke about the UV, RI, and so on, but there are various filters, and we have these narrowband or broadband filters. So narrowband filters emit very specifically light of certain wavelengths in a very small aspect of it. And usually it is used to get finer features, like the image which you see here of this nebula. You can see a lot of fine features. So if you take various narrowband filters, different filters, we get electrons coming through, which are showing different phenomena which are going on. And you have the broadband filters, which has a wider range of wavelengths which can pass through. Very often galaxies are observed in these broadband filters. And what we see here is an image constructed from 7 broadband filters. Yeah, the same object, this galaxy which we are seeing in various filters. There's 1, 2, 3, 4, 5, 6, 7 filters. And each filter gives you a certain feature, a certain astrophysical phenomena which is going on in that, right? And when you add them up, you get the composite image, which gives you the complete picture. So with this, I will stop for questions if there are any. And then we'll go on to the next aspect. Yeah, Priya?
Just ask them any questions.
There aren't any.
No questions. Okay, fine. They cannot go on. Show them that thing. Start with that. Yeah. Please post your questions. Right, there's a question. There's a question. Why don't we subtract the flat fields instead of dividing it? So the question is, why don't we subtract flat fields instead of dividing it? Speak from here. Okay. So actually the flat fields is basically varies with response. It's not an addition thing, right? So if you, for example, the sky, you have to subtract that. You will have to subtract. But when it comes to a flat feeling, it basically shows the response of a particular pixel, right? So for example, if a pixel is such that it responds 50%, in the sense, if there are 10 photons following in and it only responds to 5 photons, right? We've done uniform lighting all over the thing. And if it's responding to only 5 photons out of the 10 photons, that means it's responding to 50%. So therefore the scaling is by division and it is not by addition or subtraction. But for example, if you have to subtract the dark, because the dark is an additive feature, right? It's getting added on to the light of the star, you are adding the dark. So therefore you will subtract the dark. But the flat field is a difference in the response. So therefore the response is telling you whether when you have uniform lighting of 1, you know, you're putting lighting equal to 1 on every pixel. And if a pixel is 0.6, that means it's only responding 60%. So then you obviously you have to divide it and not add it, right? So that's why flat fields always get divided. Darks always get split, right? The other question is by Arshi. How is this composite image from the pseudo color image and how to differentiate? Which composite image? So essentially, composite images are pseudo-color images. Because for example, different wavelengths. Suppose you know JHK wavelength. You know J wavelength is a shorter wavelength. K wavelength is a longer wavelength. So you put J as blue, H as green, and K as red, right? And with that you create the composite image. So even composite images are artificial images, right? Like pseudo images. So in principle, they are the same kind of image.
They are just
About the same. About the same.
yeah, they are enhanced in certain. You can enhance certain colors artificially a bit more or a bit less, but they are basically pseudo images.
Yeah. Please post any more questions. Are there any more questions?
Is my mic working or not? It's stopped totally.
Just talk and I'll just see.
Okay, then.
Yeah. Okay. So now we'll proceed to our third part, which is again on CCDs only, where we are going to see them a CCD image through a Jupyter notebook, right? So we'll pass on. We'll share everything with you. Don't worry. So you can run it yourself later on, right? So now we come to part 3, which is the CCD through the Jupyter notebook. Okay. So what I'll do is I will first do the LCO part, and after that we'll go back to the CCD part, right? So let's go back to LCO. So like you all know, our workshop is basically aimed at photometry with LCO, and you all are going to be actually observing with the telescopes. So let's now see what is LCO. So LCO is called Las Cumbres Observatory. It's a network, like I told you, of 25 telescopes run at 7 locations. There are 7 different sites all over the world, and they work together as a single instrument. So the idea conceived by by Wayne Rosing, who ran a non-profit private operating foundation in 2005. The offices were in California, and he located the first ones over there. And so what is the thing about a robotic telescope? A robotic telescope is a telescope that makes observations, which I'm going to show you very soon. You make observations without hands-on human control. So what we do is we can upload a request for an observation, right? And what happens is you saw that there's a whole network of telescopes. So what the telescope software does is it looks for the object you are trying to observe, and it tries to define from which location of the earth will it be possible for you to observe that object, right? And therefore, in an automated manner, it actually selects which is the place at which you are going to observe, right? Computer control through robotic. The theme is that at every vision, telescope is exactly up the data obtained from different telescopes, right? So there is scheduler, which you see over here. The scheduler, it is partially automated. It gives you a certain amount of flexibility in the sense you can say to what extent are you willing to compromise on the quality of data. For example, you don't want an object which is only on zenith. You are willing to observe it when it is at lower, at lower altitudes, or if there are certain differences in the seeing, etc. You can actually request for whatever you want. So, so there is a certain good amount of flexibility also, right? Now, what makes LCO so unique? So these are 7 different locations which you can see of it. And the purpose is basically, one of the biggest aims of it is to observe transient astronomical events. So if you all remember the DART mission, the Didymos asteroid slamming, right? Now all ground-based telescopes could observe it, but only depending on their location and depending upon when it was night and day, etc. But LCO, I will show it to you, they did a beautiful viewing of the collision. And because they can sum up the data from different telescopes all over the world, irrespective of the time of the day or night, they can get the data and add it up together. So that's exactly what they did, that they actually observed it. You'll see the video is probably some of you all may have seen it. It's already available freely online, and it's all there. Also, the instrumentation is uniform, robotic, and it's very rapidly delivery of data. So for example, see that if today we put in a request for data, most probably when we meet tomorrow, then the data will already be available, right? So you can easily, the data comes in pretty fast, unless and until it's a difficult to observe this thing. But you can see, let's say you have a good north-south selection of, locations. So you have Hawaii over here, you have North America, South America. So you have all these places where you can you'll be able to access the data at all points of time, which makes it very nice. Okay. So there is what is called the Global Telescope Network, which you can see over here. And so, like I mentioned, you have the site in Hawaii, you have Texas, you have Chile, you have Tenerife in Spain, you have South Africa, Israel, Tibet, China, and you have Australia, right? And they basically have sets of telescopes, 2 meters, 1 meter, as well as 0.4 meters. So one of the, like only the basic science goal is to look for time-dependent astronomy, anything sudden. You can immediately, if you're part of what are called Global Sky Partners, which we are, so you can always contact us at any time. If there's something really immediate which needs to be observed immediately, it can be done. And like I said, since you have such a good widespread area of this thing, you can do it away. And then the other important role LCO plays is what we are engaged in just now, is a large educational component, right? That now, since we have access to these telescopes, we actually have access to instruments. It's almost the feeling of observing the telescope, which we can do with these telescopes. So that's the other important role that LCO plays. Now, each node, or the 7 nodes which I showed you, they have 1 meter telescopes. They have, some of them have the larger 2 meter ones. They have 40 centimeter telescopes where you can do photometry. So the problem is that if you want to do spectroscopy, you'll have to use the 1 meter or 2 meter ones. The 40 centimeters ones, which we can use, only let you do photometry. And that's why the focus in this workshop is on photometry, because that's basically what we can do with the telescopes we have access to. We can't do spectroscopy. So that we need this thing. So typically, what does the site look like? You have the site services, which are here. You could have up to 6 40 centimeter of telescopes. There's a storage section. And you could have for meter telescopes, you could have a 2 meter, depending on which is the site you have. 1 meter telescopes, like I told you, the instrumentation, it has one camera, which has a 4K by 4K CCD. The sad part of the story is that we don't have access to these telescopes. If we want to, we will have to separately request unmute. I hope all's fine. Sorry, there was some net problem. Now I'm unmuted. So you have various instruments on the 1 meter telescope, like I told you this, but the problem is that these instruments are not accessible to us. We have basically access to the 40 centimeter telescopes, in which you basically have a 2K by 3K camera, and with photometry and fast, auto guiding, etc. And this is the kind of data we can access, which we will try to observe, and which we will this thing, right? So I will. Yeah. Is it fine or okay? Yeah, okay. So that's again for about this thing, that it gives you excellent science, engineering, and education, right? So I mentioned this already. So what we are Global Sky Partners, and the project we'd actually put in was for star clusters, but essentially we can also accommodate different kinds of observations if you are interested in different kinds of this thing. Yeah. Yes, we had some network problems, but it's fine. Okay. So now what we're going to see is, yeah. So one important thing which I mentioned earlier to you all when we did the photometry part is that I told you that when we are observing things, we also need to study what are called standard stars, because we need to correct our instruments, right? What we observe in terms of magnitudes with the magnitudes of standard stars. And I'm not going to go too much in the details of this, but I'm just going to briefly tell you that, for example, if you're observing with the B filter, right, what you would apparently see would be something, and the actual value would be something, which would actually vary. So the actual value obviously varies on some kind of a 0 point, which is given over here. It also varies sometimes on a color factor, right? There could be a color term. That means the correction could be different for redder stars or for bluer stars. And it also could depend upon the air mass, which is X. So if you actually see the formula, it will look something like this. So for all the magnitudes which are derived from the telescope, you will see that the magnitude what you're observing is what is called the instrumental magnitude. And the other magnitude which you see is the standard magnitude. And there could be a difference between the two. So there could be what is called a 0 point, which I showed you in the previous equation. There could be also a color term. That means it could vary depending upon the color of the star, whether it's a red star or a blue star or whatever kind of star it is. And it can also vary on what is called the air mass. I'm sorry I didn't put a slide on air mass, but basically air mass is something which tells us the height of the object or the altitude of the object from our horizon, right? So typically if you have an object at zenith, right, which is right on top, 90 degrees, right on top, so it's air mass 1. In that case, that object goes through a minimum amount of atmosphere, right? So if you'll always see that when you look up at the sky, you'll always see what is overhead is the clearest part of the sky, because that goes through minimum amount of atmosphere. But as you come to lower parts of the sky, then the amount of atmosphere the object has to go through is much, much larger, right? And therefore, there is much more distortion or loss of light. So therefore, often you would have observed that if you look up at the sky, what is on zenith, which is air mass equal to 1, you will see those objects very well. But as the object comes down towards the horizon, you cannot see that object very well because it has come down, right? And therefore, what happens is we correct all magnitudes to air mass 1, right? To what it would be if it was at zenith. And you can actually go through this website with this location over here. This shows you the different photometric coefficients. The coefficients, by that I mean the Ci, the K, as well as the Z. All these factors, they can be actually seen on this website. What is the value for LCO? So what LCO does is that every night between observations, they observe standard stars so that they recalculate the values of these coefficients. So that when they observe, they can give you the exact value of the coefficient and correct it so that your magnitudes are in standard magnitudes, right? So that is what it happens, but it happens in such an automated way that you will almost be unaware of such a thing happening, right? But this is just to keep you aware that this is something which is happening at the telescope end, which actually, corrects the photometry, converts it from instrumental magnitudes to standard magnitudes, right? And that's what it is, right? So here I just put a snapshot of the values of the coefficients which are available on the LCO site. So here you can see these are the 0 points, and these are for the different locations, right? For the different locations for different instruments. This is the Australia site. So it's telling you this is the 0 points, this is the color term, this is the other terms. Like you see, the color term does not contribute so strongly, but it's still important. The 0 points and the air mass terms are also, right? Now we'll come up to the main thing, which we are going to talk about, which is called Banzai, okay? So Banzai actually stands for Beautiful Algorithms to Normalize Zillions of Astronomical Images. So what is Banzai? So Banzai essentially is a pipeline, okay? It's a pipeline so that when you observe with the telescope, you observe with some telescope, then what it basically does is it converts it. It basically converts all this, what we call this raw data, right? So it basically converts all the raw data and it gets it in a form which you can use. So what it basically does, you can see this pipeline over here. This basically shows the flow of data from the end of exposure to the users, right? So once the shutter closes, right? I think I forgot to mention to you, but astronomy data or images are kept in what is called the FITS format, right? You must be familiar with images being in the BMP format or the JPEG format or the PNG format. But in astronomy, we use the FITS format, which is the Flexible Image Transport System. And basically, what happens in that is the first thing is like you heard about digital images. So a digital image is just like a matrix. It's an XY matrix which has certain counts, right? So first thing of the image is a digital part which has the counts, the XY counts, right? And that is very necessary because all digital images are to be considered like matrices, right? So what you do is if you're adding matrices, then element by element you add matrices. If you are dividing matrices, you divide it element by element. Similarly, you can multiply the same factor into every element of the matrix. So a digital image essentially is that matrix. But added on to that matrix, what we also have is a header. A header file is a file which has information about the image. Okay. For example, it has information that the image is taken from a particular telescope. It's observing a source with a certain right ascension declination. It has an exposure time of say 300 seconds. It was observed with the B filter. So various important data things, instead of keeping it separately, right? What is done is it is packaged along with the image. So you have the digital data, first of all, which are the counts. Then you have a header file, which has the header information. And now this has even progressed further where you actually do things like, you even have data cubes. You can add up these images together, right? For example, if I have an image of the same thing in say 10 filters, I can stack all these images together as different layers so that all of them are sitting together with the same header file and the same header information depending on where I observed it from, right? So in short, the Banzai pipeline is basically, the requirement of it is it takes in the data and gives it to you in a form where you can use it. So what happens is you start off with the FITS data, right? And then the FITS data, once the shutter closes, the ship data is sent to this FITS queue. Then it goes to LGO-GT. This is the global telescopes, the headquarters. It's sent to the headquarters. And then from the headquarters, once it's arrived, then this Banzai pipeline. So the Banzai pipeline is also available on its own GitHub page on the internet. So it's freely available. If you want to Google, the ones of you who are interested, you can Google GitHub Banzai and actually find the Banzai pipeline, the data. So what happened, the whole pipeline, so you can actually see what is Banzai doing to your data, right? Because you just heard about CCD data, right? So what does Banzai require to do? First of all, it needs to do bad pixel masking, find the bad pixels which are there in the image. So you mask off all those pixels. Then you would, for example, need to do dark subtraction, subtract all the darks from it, right? Then you will do flat fielding, right? You do dark subtraction from the flat field also, and then do flat fielding. And then what Banzai also does, which is something very important, is it actually creates a catalog. So for example, you observed a set of galaxies or stars or whatever. Banzai, it takes in this raw data to give you processed data, which already has a catalog. So you can see the objects which you are observing in the form of a catalog. By a catalog, I mean it will give you right ascension, declination, its brightness, its error in brightness, and all these factors, various other factors about those objects. So once you have your catalog, you already know your objects, and you can directly use this to do some kind of science with it, right? So a good amount of effort has been done in applying the Banzai pipeline so that it, does its job. Now, in case there is a user who's not happy with Banzai, right, who does not like the pipeline, the data is also available in raw format. So if you want, when you download your data, you can take down the data in raw format, analyze it yourself, not use the Banzai pipeline. Or from the GitHub page, you download the Banzai pipeline code, make whatever changes you want to the code, and then run the whole thing again, right? So there's a lot of freedom in that sense with the Banzai pipeline. So like I told you, the Banzai pipeline, what it does is bad pixel masking, bias subtraction, dark subtraction, flat field correction. Then it uses the source extraction software, which is called SEP, source extraction and photometry. And then another important thing it does is it's called astrometric calibration. That means for every image, it gives you the RADEX of all your images. So you know exactly what are the WCS or the world's coordinate system of all your objects, right? So all that is also done by Banzai. So Banzai is something really very useful for all users of LCO, and you should be aware of it, right? So this is just a repeat of the same thing, and I will this thing. So then I can show you the data archive at LCO. Are you ready with the CCTV?
Data archive, then I show how to read through the data.
Okay. So now I will actually share screen over here. So let us go on to this. This is the LCO website, right? And here you can see there is a good description of the Banzai pipeline, which you can see over here, which is mentioned all over here. And you can read this, right? Now, if you want to access LCO data, you can do it very simply. It is done over here. Those of you all who have laptops, you all can try it out. So I will just do this. Yeah, go to this. Just go to archivelco.global, right? So I will just do this. So you just have to go to this website, which is called archivelco.global. What I'm going to do is I'm going to share this website on the Zoom chat, right? So on the Zoom chat, yeah, here's the Zoom chat. This is the website, okay? Actually, you don't have to have all those things. You just need archive LCO. 1 minute. This will not work, maybe. Let's just try this out. So you'll say, this is the easier way to do it. Yeah. Oh God, no, sorry. Went into YouTube. Yeah. So please go to this website, archivelco.global. But 1 minute, before that, I'm going to show you something else. 1 minute, I'm sorry. But before that, I wanted to do a demo and show you how do we actually do observations, right? So first, let's just see that. And after that, I'll show you this part. Okay. So here, for example, if you go onto LCO, I have a login. So I will go on that. I can maybe. I was trying to make a login for participants. I'll do that later. Okay. So I'll first do my own login and then do yours. Right. So what happens is, like you see over here, this is where I actually put up my requests for observations. So let us, for example, I have a login, and that's why I could log in. I don't think you all can log in, but I can give you all an ID with which you all can log in. Okay. So I'll send that to you all in email, and you can try doing it. So if you want to submit an observation, right? Let's say you want to submit an observation, and I say, for example, I want to observe, for example, a cluster, right? And this thing will come under this thing. This is a proposal which is with LCO Education Development, and that's how you have it over here. And here you can see, you have to, for example, the object you want to observe, right? Say you want to observe and get an image. Spectrum we can't do because for that you need a 1 meter telescope. But you see there are other telescopes. We are going to look at the 0.4, so we are going in for an image. And here, for example, we decide what is the exposure time. So let me say, for example, I'm saying 300 seconds. I can choose the filter I want, for example, B-band filter, and I can choose an object. For example, I can choose M51. I'll have to change this. I'll say this is a sidereal object, right? There are times when you may need to use non-sidereal. Is that recently when I was also trying to observe the dart, this thing. So what is actually telling you that we already on the LCO archive, they have so many existing frames that you can access of M51, right? But we can say, no, we still want to observe it. And therefore we say we still want to observe this object. And I say, you have to state what is the period in which you want to see it, right? So if I say I want to observe it today between 9:53 to, this is in UT, till tomorrow. I'm giving it a 1 this thing. So I can actually try the target visibility calculator. And this is basically going to tell me whether my target is visible or not, right? So I can see it and it can tell me if it is visible or not. I will just see this thing and I can see this. Okay. So here is my visibility. So you can actually, if you want to check if this object is visibility or no, you can actually put it over here and see it, right? Now you can see that there's something called a cadence. That is, supposing if you want to actually look at a variable object, you can add a certain cadence and actually observe it with, we will try that out again tomorrow, but I'll just now show you this object and we can put this thing. So now we are requesting observations of this object with a certain exposure time using this telescope, right? And though it's telling us that, now you can also apply a air mass limit. Like I told you, the air mass is 1 when it's down, 1 right on top of zenith. This one is taking maximum air mass. You can, for example, state that I want it to be with maximum, I can take so much of an air mass. Similarly, if the moon is out, we know that just now the moon is out, tomorrow is full moon, and therefore it's going to tell me the minimum lunar separation. So supposing if I say that it should be at least 30 degrees away from the moon, but it is within that period, then my observation will not happen, right? So we need to know whether this object is over there, right? So it can actually, depending on that, it may observe or not observe. So you should check onto that thing. And you can see over here it's written, according to constraints of the request, the target is never visible within the time window. Check that the target is in nighttime sky. Consider modifying the target window so we can change it. So I will change this thing from M51. Let me make it, for example, M4, right? This is a globular cluster. I'm changing it to M4. So what happens is the robotic thing actually tells me the availability of my object, right? And now I'm saying, when I'm saying M4, it's telling me the stuff with M4. I continue with this thing and you can see here, now it's showing me a visibility thing that if I were to observe it, right, from this telescope, this is the Cerro Tololo one, this is the Siding Spring one, then Cerro Tololo, it's not very good visibility. You can see it's happening at this kind of air mass, 1.6, 1.5. It's not a very good object to observe, right? Or if I were to observe it, the second window, if I were to observe it, I can look at it like this, but again, you can see it's not a very well observable object. So what you can do is you can change the object which you are observing. So for example, we'll go in for some other object. Let us take another object. For example, I often take NGC 1960, but this is a comet. Okay, let's take NGC 2384. That's another star cluster. Now what it's going to do is interactively, see, it's telling you what is the visibility of this object, right? So when I say this, it is still searching for coordinates, and I hope you can see my screen, right? So in short, now you look at this object. It's actually telling you it has a little better visibility from Siding Spring. It's right. So here again, you can see that this is my thing. And with this, I can submit a request. So I can submit a request. And it's actually telling me that of the time I've got, it's going to take 7 minutes, 2 seconds. And I can say, okay, right? So here I can submit a request. So here I've shown you how to submit a request. But after the request comes, right? I will now show you. Yeah. So after you submitted the request, you see here it's giving me the details of the request. It says starting from today, ending tomorrow. right? It's ending tomorrow. It's for 24-hour window. It's going to look for my object, give it a 300-second exposure, and it's going to go with maximum air mass, minimum lunar distance of this, and it's going to acquire it, right? So in that, you can see over here the acceptability threshold. That means it's telling me that most probably 90% it can do this thing, it can give me my data. So it plans to give me my data, and that's how it will, this thing. Do we have any questions, or do I proceed? I'll just look for any questions. I'm sorry, we seem to have some net issues today, but are there any questions about this part of how do you acquire data with robotic telescopes? Right. I will give you my login and my password. I'm sorry, there's really some problem today. So I will send you a mail, which I will send you the username and password, and you can try doing your own observations. But obviously, please don't do more than 300 seconds, right? Because Rita, you have a question.
Can we
I'll
cancel
unmute you
after
so you
submitting?
can.
If something happens and you need to cancel it, is it possible to cancel the observation?
Rita, you have a question?
I'm asking, is it possible to cancel the observations after submitting it?
You have permission to unmute yourself. You can ask.
I'm unmuted. Hello?
Does anybody want to ask any question, or should I proceed?
I'm speaking. I'm unmuted.
Hello?
Can you cancel the observations?
Rita, you want to ask a question?
I'm speaking.
Ma'am, she have unmuted.
Everyone can hear me.
Yeah. Sorry,
Yeah,
there
we
was some
can
audio
hear you.
problem also.
Yeah, we can hear.
Oh, there are questions. Very good.
My question was.
Yeah, Rita, now you can ask a question.
After submitting the request, is it possible if something happens to cancel it?
No, I can't hear you. Sorry, can you just type your question? Can you type your question? I can't hear you.
I typed it in the chat.
Yeah, I can. I saw it. She's asking observations can be cancelled. You mean to say after you put in the request, then cancelling it? Hello, that you mean to say after putting in the request and cancelling it? Actually, I've never done that. Yes. I can check. I'm not too sure how that can be done, but maybe it can be done, because there are always people on that end who are, online and who do respond. But I don't know. There's no button. Yeah, but there is no button I know of which you can press, which will cancel the observation. For example, I've put in this proposal, right? I don't know where in this location if this is the proposal, where can you actually cancel it? But that's a good question. I can actually ask those people. I've not seen anything where you can cancel it. So I'll have to check. I'm not sure. Any more questions? Are there any questions? Yeah. So the next thing I wanted to show you. Yeah. So there is no. I don't think there is a. Yeah, I don't know whether there's a default option to cancel. No, I don't know. I'll check. Okay. But what I wanted to let you all know is that if you don't do that, there is a lot of archival data already available in LCO. And that is what I would really like people to access or avail, because there's a lot of data already available. So you just have to go to archivelco.global. I'm going to share this website with you all on the chat window, right? And I would request everybody to actually get onto that, right? Right. So I was searching for something else, so that's why there's stuff over here. But in short, what happens is you can actually use the LCO archive and actually look for objects from the archive. So here, if you, or you go from the LCO page, you can actually go here and what is the, yeah. Okay. So what we are going to do today, if many of you all have laptops with you, what you can try out tonight, rather that's a better option to do. What you can try out tonight is go to the archive lco.global page, right? And you can actually look for an object. When you put the object, supposing if I'll put one of star cluster because that's what I work with the most. Or you could put any object, supposing you put M51. Yeah, you can actually look for data for a given object, right? Okay, no, it's not coming here. You can actually look at proposals from here. If I can look for my proposals, or you can go for any other proposals which are listed over here, right? So I would actually suggest that you, okay, YB, you need a login. Can you create a login, or is it letting you create a login? Can the ones who are sitting on laptops, can you see, is it allowing you to create a login? Or do I have to give you one?
Ma'am, I tried, but it's not happening. I'm trying again. I will let you know.
Okay. But it's not letting you create a login. You can't create a login. Then I will give you all my login. If it can't, you can't create. Okay. So then create a login where you log in with my email. Put it as priyahasan@gmail.com. That will be the login. And the password is a big secret. Hence it's secret at 123. Okay. So please everybody try to log in. But please be this thing, I'm giving you access to all my thing, right? So please don't misuse it. Log in as this. Log in as priya.hasan at this thing. And this thing. Are you able to log in? Are people able to log in or no? Could you please let me know?
Ma'am, it actually allowed me to log in, so I have made my separate login and I am logged
Okay,
in.
very good. Very good. That's very good. So now what we are going to do is our final step, right? That you all log in. If you, who's that who could log in? What's your name?
I am Dhanraj.
Yeah, Dhanraj. So Dhanraj, you managed to log in, right? So once
Yes,
you
yes.
log in, right, you can actually, if the others can't, have given them the password, or I will share data with them, right? I will share data with them. So what you can do is you can actually have a look at the data available. I can, let me just, okay, simplest one, okay, let me show you for standard stars. So for example, here, you look in for proposal all, and here go in for, can you do it? You can do it. Achha, let Okay, so I'm going to send you all some data, okay? Because at present, since people are having a problem in logging in, I'm going to email you all data after today's session, okay? But for homework, what you can do is this data which you get, it basically comes in the form, I hope you can see my screen. Can you see my Finder window?
Yes, ma'am. Yes, ma'am.
You're seeing my
No,
Finder
no, no.
window?
Find a window is not coming, ma'am.
Okay, then I will just stop and I will say share and I will say desktop. Now we have 20 minutes left. So you can see over here, I'm going to send this data to you, this data. So when we download it from the Banzai pipeline, okay, I want you to see this because this is the result of the Banzai pipeline. It will give you a zip file, okay? So I will mail you this zip file, okay? And from this zip file, when you want to view it, okay, you will see it is basically made up of various files inside it. Okay, I have, this one is a smaller one. I should show you a better one. 1 minute. I'll just a minute. Just give me a minute. We'll do this more in detail tomorrow, so don't worry. I'm just hurrying up a little bit. I will actually show you this kind of data. For example, this is 2. You get into this, you'll find various files sitting inside it. Okay, there'll be various files sitting inside it. And the 91 files, these are the files which are the analyzed files. Okay. Now, what you all need to do for homework today is you need to download a software called TopCat. Okay, just say TopCat. You'll find this thing over here. I'm sharing this link with you all on the chat window. This is a Java-based software. So all you have to do is, I'm giving it to you on the chat window. Please have a look and download this software, this Java-based software, okay? And tomorrow I will show you how do we view the Banzai pipeline files. Number 1, using TopCat, right? This is made for people who are not very comfortable with Python coding. And number 2, we will show you how to analyze the Banzai pipeline data using Jupyter notebooks, okay? So I will do that tomorrow. Today you'll install TopCat. I will send you a data file. And yeah, so there is no problem in this for Linux or Windows because TopCat is Java based. It will work on Windows, Linux, whatever you want. There's no problem at all. So your OS doesn't, yeah, it'll give you a jar file. So all you have to do is on your system, you'll have to download Java. So basically you'll say TopCat, Java minus Java minus jar, right? So you'll say Java minus jar. When you download the file, you'll say TopCat.jar, right? This is if you have a Linux system, you will have to give this command, Java minus jar TopCat.jar. If you are on a Windows system, you just double click it, it will connect it and it will run. Okay, so that's what we're going to do Banzai pipeline tomorrow. But today now we have a little bit, which now Sir has managed to set it up. So we'll show you CCD images through a Jupyter notebook, right? So now let him share his screen. I'm going to stop my share and I will continue with Banzai pipeline tomorrow, right? You have 20 minutes.
Share. The other one, Vijay Manu.
Just a minute. Where is it?
Should I use your mic?
Yes.
Hello, I think you can hear me.
Yeah, I hope the audio is fine. If it's not, please write in the chat. Yeah. Sure.
Yeah, so I will show you a little bit on how to handle these FITS files, the files which you're going to download from the LCO directory, and how to handle them, how to read them in Jupyter Notebook. And then we'll use AstroPy, which is a module for astronomy, doing astronomy through Python. And like Priya has shown you, you make a directory and download the data. For example, you can see this, yeah, from the location I've downloaded. This is standard stars, right? You get a post of, you get a zip file. Basically, what you will get is a zip file, and when you blow it up, you will get a series of files. Okay, and each one has an extension fz, fits.fz. Just be very careful. This is a dropping about over.
Okay,
Yeah.
fantastic.
Can you? Yeah. Okay, so these are the ones you blow it up, you find the location where you have it, and this is how you can read. So a fixed file format is, it's not just a single image file, but it is stacked up. These are fits cubes these days, where you have one can be a science image, one can be bad pixel mask, one can be the errors on this, and various things, right? So you will have to install Anaconda. And how many of you are familiar with Python? So install, yeah, just say if you are all are familiar with Python. If not, then okay, so many are familiar with it. So once you have Python, as you know, from the terminal you type Jupyter Notebook and it opens up the notebook, and there you have to put these commands. So here are some basic commands which we'll share with you, with which you should be able to access these fits files, right? So this first line, percentage matplotlib inline, basically it tells you to plot things within this within the Jupyter notebook right there. Yeah. So in the newer versions, this has become redundant, but then you have to have this AstroPy installed. So you can pip install AstroPy, right? And once it is done, so I'll create another block here and I'll show you how you do it. So you just say pip install AstroPy. Here in my case, I already have it, and you have to shift and enter. So here you will see that requirement is already satisfied. This is this which is coming. And if not, then it would install it, and then it will ask you to restart the kernel. And on top, you will see there's a kernel here, or there's a circle here with which you can restart the kernel. Okay, this is for those who are installing it for the first time. So I'll comment that. And once AstroPy is installed, you have from AstroPy IO import fits. Since these files are in fits formats, this is the utility you require. This is the task you require to read fits files. And then from AstroPy, we also import WCS, World Coordinate Systems, right? And we also have import ApplePy. Okay, and then you control enter, and then the next line here, line 3, it shows you how to read it from the specific location. So from the point where I have started my Jupyter notebook, there I have a directory called LCO data. In that there is a subdirectory standard starts, and in that you have those various files. And like Priya mentioned, you have to use this E91. Yeah, these are the files which you require. You can dip into the other ones and see to what they are. So here we are reading this particular PITS file, pits.fz, right? So you need write the whole thing and give the path to the location where this file is located. And we are storing it into a variable name called file name. So this is what we do, and it reads the data, and then we will read the header information. So I have the command called, if I say fits.open file name, and when I run this, and I'm storing this this file, right? This is the variable name file name, and I'm storing the fits.open output into the HDU, the header data unit variable which I have defined. And when I do HDU dot info, you will see this information which comes in, which shows it is showing that it has 0, 1, 2, 3, and 4 stacks in it. 0 is the primary one, primary HDU. Then 1 is the SCI, the science image. Second, see the labeling is from 0, 1, 2, 3, and 4. Second is 2 is the catalog. 3 is the bad pixel mask. And the fourth one is the errors. Okay. And it shows you the science SCI. I'm seeing it is 3054 cross 2054 dimensions. The format is float, and right. So you have all this information which is you get from HDU info. Then you can start reading the header information in each of these. So when I do HDU square bracket 1 dot header, I get the header information which is just bear with that flashing because I can't help it.
I don't know what's causing
I don't know what's happening, because if I meddle around, then the whole thing may go. So we'll be sharing you this file. So once you download a fix file from the site which Priya mentioned, you can use these commands to. Yeah, I'm opening. I open. Okay, so I can shut this in. Yeah. So you see the header, the data unit, header data unit 1. Header it gives you this whole listing. So in the header you have all this information. So these So these header informations give you all the required information which you require. And similarly, you can see, right, what telescope, which location, and so on and so forth. So this is, so this is the first. And then similarly, you can put HDU2 header, and it says it's a table, right? The 2, if you remember when we saw the info, header.info, you notice that it was the catalog, right? So you see here, second one is the catalog, right? The first one is the science image. So when you look at the header information for the second frame, you get the details of it, that it is a bin table and so on and so forth. Okay, and so on. You can see the other ones. So now you can use this world coordinate systems to fit to your HDO fits file. And this is the command you use, WSC, what's the command? Yeah. .WCS HDO2 header. And then we convert the 0th field, we call it the x-axis, the first one as y, and you are converting xy into the RAN deck. Okay. And then we apply the APL PI library to display the fits image with the photometric data overlay. And these are the commands which do that and which as well. So this is the image which we have. Right destination declination, and you see scale or heat or different maps, right? So for now we will do this much. So for this, what you have to do is to install Python, use Anaconda to install. It will install most of the required modules in it. You will require Matplotlib and AstroPy and so on. And if you are running these and if you are having issues with any of the commands, you just have to pip install and get them going. Okay. So
we just take a few. We'll take a few questions before we wind up. And what I'll do is I'm going to email you a data set. We'll email you this Jupyter notebook, and you can try out with it till we meet tomorrow, right? So till then, do we have any questions? Let us. We have about 3-5 minutes left. So do we have any questions? Yeah. Okay. Those who have no Jupyter notebook, yes, you can use Google Collaborate. No problem. Use Google Colab. That would be a better option. Can you elaborate more on the errors? Whose SS? Which errors are you talking about? Could you unmute yourself and say? You have permission to do so. Somebody who's asking about errors. Can you just say what errors are you talking about?
yeah, so the errors, see the issues you have with the CCD chip, which is there.
Sorry, there's a big
those errors
echo.
are given in the file, right? Because some of these pixels can be oversensitive. They'll load more information and require more light than. Right, so the BMP HDO is for the bad pixel mask. Some pixels, certain columns themselves can be totally bad, or you may have errors in the observations. If there are some issues with it, they are given in the. Yeah, can we have the code?
Yes, I'll be mailing this code to you just now, very soon, with a sample data set. Okay, we'll just be mailing that to you soon.
Okay, sorry, there was
Even
just a very.
Yeah, we'll mail it.
Sorry, Miss Hasan.
आकृति में बन के। Yeah, so yeah, basically we realized both the mics were closed. I will share one more Python file in which you can construct synthetic images. For example, here I am constructing a synthetic images. I am using numpy.0. It's basically a matrix I'm constructing with 1,000 rows and 1,000 columns with all zeros in it. And I am saving it as an image, right? I'm calling it a synthetic image. And when I'm plotting it in the grayscale, I am getting this thing because they are totally 0, 0, 0, 0 all around. Then we'll add some noise into this and add this synthetic image. To that, we'll add the noise which I have constructed in this block. And then when we plot it, you will see this is the one, right? So these are synthetic ways of creating these images, which you can play around with that, add different noises, and the same procedures when done in reverse will do your cleaning. So you have an image with noise in it, and how do you subtract the noise? You create a Gaussian noise, remove from that, or yes, so how to create dark frames, how to create flat fields and so on. You are creating, in this you have created dark exposure of 100 seconds, and I have constructed this, and then we'll subtract it and see, and no audio at all.
Again, no audio. I think audio was there.
Is the audio there?
Yes, sir.
Can you hear? Hello?
Thanks to organizers, we're doing today's. Yeah, excellent. Let's stop.
Yeah, so let's stop for today.
And see you
Sir,
tomorrow at 2 o'clock.
ma'am, I have.
We'll meet tomorrow at 2 o'clock. We'll share these notebooks with you and the links, and we'll meet tomorrow. Bye-bye.
Bye. See you tomorrow.
Hello.
Yeah, okay. See you. Bye-bye.
Hello, ma'am. Can you hear me?
I think they're extremely experiencing bad network. I'm not sure if you can hear me yourself.